Well, friends, season's greetings from our channel, Total Output Power Solutions. Today, we are discussing about performance improvement in AFBC boilers. We will be discussing the same and some case studies also. So the discussions will be about some case studies with problems and solutions related to AFBC boilers. Now here we are discussing about the problems in Dolachar and coal-fired boilers when both are fired together, Dolachar as well as coal. Generally, this type of fuel is used in boilers in sponge iron industries. So Dolachar and coal are fired together in boilers used in sponge iron industries. The Dolachar contains iron particles which are heavier. As one can expect, the bed can have segregation of particles to the bottom of the bed. In many cases, the operators ignore this. Once a bed lands into segregation of particles, there is no way out in case of a flat distributor plate design. Only open bottom designs can pull out the oversized particles which settle at the bottom. Alternately, sloped distributor plate with many drains can help to control the particle separation. Particle separation, when takes place, preferential erosion of bed coils is seen. Then in case of Dolachar fired boilers, in these combustors, the generation of bed ash is also more. We may not find a requirement to add bed material. Except for a fresh startup, we may not use iron-free bed material. Bed coils in these boilers call for early replacement and the availability of the boiler is greatly disturbed due to unscheduled shutdowns. In underbed firing system, feed system, the erosion of bed coils is localized, whereas in overbed, the erosion is not so, provided we keep removing the heavier lot. If heavier lot is allowed to accumulate, the bed coil erosion is of different kind. The coil is seen eroded in between the studs as in the photograph. There is a gross erosion of bed coil. All these troubles are related to iron accumulation. The coil here you are seeing is eroded in between the studs as in the photograph. There is a gross erosion of bed coils as you see in the photograph. The studs erosion that results in heat transfer in the bed coils. You can see the studs in the original studs, and if the erosion is there, then you can observe these results. The fluidization is disturbed when there is a risk of localized hot spots, that is called as agglomeration of bed material. Agglomeration can lead to operational issues and reduced combustion efficiency. This increases the need for frequent cleaning and maintenance, leading to less downtime and lower operating cost. Reducing the fuel flexibility, reducing the overall efficiency. Uh, the stud type bed coils contribute to the overall efficiency of the AFBC boiler. So the solutions for these Dolachar and coal-fired boilers could be the solution could be a continuous bed ash iron removal system. The bed ash must be cooled and discharged to an automated magnetic separator system and oversized screen system. The screen blade material should be recharged to bed through a bed material silo and feeder system. It is advised to resort to continuous bed ash removal and recharge system. Now we go to the case studies related to fluidization. Now this was a 90 TPH coal-fired AFBC boiler with overbed feeding arrangement. The boiler was restarted after a shutdown from cold condition after 5 days shut period. The bed material was not changed. Whatever remained before the shut has been used as such. Naturally, we can expect that bed particles range will be from fly ash dust to coarser ash. As this boiler was provided with overbed startup burners, the height of the bed material had to be kept to 600 to 700 mm in order to cover up the bed coil. The burner was put on for 3 hours to raise the boiler pressure slowly and to promote the circulation in bed coils and other evaporative circuits. In overbed burner startup system, the bed never gets heated up beyond 150 degrees centigrade. The airbox pressure was raised to 800 millimeters of water column and the coal feeding was done. The powder content in the bed material got separated to the top and gave a picture as if the bed was fluidizing. The bed plate design was checked up for MCR pressure drop. It worked out to be 300 millimeters of water column. That means nearly 600 plus 300 equal to 900 millimeter of water column. Air nozzle pressure drop will be required to set a cold fluidization. So when the FD fan cannot give 1500 millimeters of water column, the question of thorough fluidization cannot be achieved. So there are temperature differences between the bed thermocouples even after 12 hours after startup. Now in this situation, whatever fluidization which was observed was clearly a regime of fluidization with two sets of particle groups. Now to correct the situation, the bed material was drained from several drain points simultaneously to bring out the coarser fraction of material at the bottom. After 4 hours, we had seen that all the bed temperatures reached the same value and no temperature differences were observed. So further it was advised to use finer bed material, that is maybe minus 1.5 mm sand, and also not to discard the finer fraction of the bed material, that is less than 0.5 mm. Now in the second case is also related to fluidization. This is a coal-fired AFBC boiler with underbed feed arrangement. Within 2 months of changing over to new lot of imported coal, the plant suffered bed coil erosion. The unit experienced severe iron accumulations in bed as such. The Fe2O3 was around 33%. So the source was discovered and the source was found to be the high iron content in fuel, imported coal itself. So a model calculation was done and it was proved that we need to increase the fresh bed material feed rate to 25% of fuel feed in order to limit the iron in bed ash to 5.6%. Incidentally, more the iron content in coal, the ash fusion temperatures could be lower. The bed may begin to generate clinkers as well. So use of mechanized bed material screening system, regular sieve and ash analysis of fuel, regular measurement of sieve analysis bed ash, frequent check in iron content of bed ash and bed material would help to improve and get the best from these AFBC boilers. In another case study, this was a rice husk fired boiler and it was observed that severe polishing of bed tubes was there. The generation of steam had also come down drastically. Definitely the problem was related to fluidization. Now rice husk fired boilers need regular makeup of bed material. On visit, it was found that the bed ash drained from the bed was heavier. So when this was the observation, so it was the bed ash was checked with the magnet and it was noticed that the bed ash contained 40% of iron. So the source of iron it was also found and the source of iron was found to be the bed material itself. The crushed refractory as explained earlier is made from crushing used bricks removed from iron melting furnaces. Naturally, the iron content in the crushed material has to be more. The vendor did not separate the iron, which was the normal process used for making refractory bricks to meet the IS-8 specification bricks. So it was advised to change the bed material to fine reverse sand. Now case study number 4. In this case, this is a case of 100 TPH boiler which was designed for high DP drop operation by design. The cold fluidization was checked with a bed height of 300 mm and with air box pressure of 1000 mm of water column, but the bed did not fluidize. So the customer was requested to change over to finer bed material for starter, but the bed did not fluidize even after 12 hours after the cold feeding was commenced. It was recommended that the fresh fine bed material has to be added to large extent and simultaneously drain the bed that did not fluidize initially. So in this case, the cold fluidization was being ignored by it is ignored in many of the recent boilers which were provided with overbed startup burners. When the bed is designed with hot air generator, and this would not have been a problem. Had the boiler been provided with charcoal setup burner lances, the boiler would have never started. It would have experienced clinkering every time. So high DP drop in bed would give problems in setting the cold fluidization. Cold fluidization inspection should be a part of the startup process and cannot be compromised. So it was advised to get the entire set of air nozzles replaced with higher diameter holes to have the cold fluidization. So the main focus should be on the fluidization. The what we should do for this, for the fluidization: measure and maintain the adequate distributor plate pressure drop. The quality of fluidization should be good, ensuring there are no defluidized zones. This cannot be ensured by visual means. The distributor pressure drop becomes a vital factor to ensure this. When the DP drop is less than 75 mm of water column, the coarse particles begin to settle down at the bed bottom. In an ideal case, DP drop should be one-third of the bed height. Defluidization or settlement of coarse particles will not be visible from top of the bed, as the fine bed material would continue to fluidize. So setting of coarse particles can also damage bed coils. This leads to localized erosion of bed tubes. This can happen even in overfed AFBC boilers. Providing studs does not help. Bed coil erosion continues. You can see the figure in the next slide, the bed coil erosion, and here you will see the bed coils, and they have the erosion at these, generally at these places. So when the DP drop is less, the bed coarse particles settle at the bottom of the bed, and that too at a particular site. So that has been marked in this figure. You can calculate the DP drop to be P1, P2 minus P1, and you should measure this always. Now we talk about bed slumping. Now slumping of the bed is done to meet the steam demand. It is not correct to keep the same compartment under slumped condition. In the slumped bed, heat transfer to the bed coil becomes less. The circulation of water ceases, and this may result in high pH corrosion or caustic gouging or settling of iron oxides, corrosion products in such bed coils depending on boiler water chemistry. You can see the figure of the bed coil, a cross section of the bed coil. So this is the cross section at AA, At AA cross section you can see the tube section, and it has an inside erosion, as you can say. This may be because of the caustic gogging attack on if the compartment is idle for a lot of time. The possible solutions could be: try to avoid bed slumping as far as possible. Try to avoid the same compartment for bed slumping. You can use different compartments for bed slumping. Maintain the boiler water chemistry. That is one of the most important reasons. You should maintain the boiler water chemistry to the best possible limits. For this, maintain the WT plant. The bed slumping, another operational thing may be you should care for shutting PA damper in idle bed. When the bed is idle, you should close the PA damper. If the underfed feeding arrangements, there is no physical partition above the distributor plate. When a compartment is slumped for load control, particularly for longer duration, it is necessary to close the PA damper in slumped compartments. If you leave the primary air damper full open in the ideal compartment, the ideal compartment will lead to bed coil erosion. It is the tendency of many operators to leave open the PA line dampers for the fear of line choking. The bed material is continuously thrown at the bed coil because of the PA damper, and that is the erosion is taking place. Now another, you should care to use the air vent wall in the ideal compartment. If you have a air vent wall, so use the air vent wall in ideal compartment. Slumping of a compartment is necessary, as we have already seen, to take care of load reduction while while startup of the combustor. You are also it is under the slumping. The compartment is slumping. There can be clinker formation if the fuel spillage is present in the ideal compartment. In certain boilers, the fuel feed point may be close to the border of the adjacent compartment. For the clinker formation, there should be air flown in the ideal compartment. The compartment dampers may not be leak-proof. For this reason, automatic air vent valves are provided in compartment air box to enable venting of the passing air from the compartment damper. If the valves are to be manually operated, the same must be done. Needless to say that the leaky damper will have to be attended. You should attend the leaky damper, or if the damper is leaking, open the air vent valve. Clinker formation over the bed in the ideal compartment, you can see the figure. In the figure, the ideal compartment is there, and over that you are able to see the clinker formation is there. And you can air vent, there are vent walls, so you can use the air vent walls so that the air vent walls can be opened if the compartment is idle and the dampers are passing. The one more care you can take care of the idle bed. At times it may be necessary to reduce the system production rate. This is the steam production rate. This is done by slumping compartments. Continued operation of slump bed may result in shallow bed height in the operating compartment and leads to defluidization. This happens particularly when the bed size is smaller. The bed height in the operating bed becomes less when it spills to adjacent slump compartments. So it becomes necessary to alternately activate the slump bed to bring back bring the bed height back to normal. So friends, thanks for watching. Hope you have enjoyed this session. We will discuss about some more points, some more tips for trouble-free operation of a AFBC boiler in our next video. Simultaneously, we are also discussing about a simulator, and that video will also be posted in the next one. So please like, subscribe and share and comment also. This is and goodbye from Total Output Power Solutions. Thank you very much.